Here are solutions to homework set number 3 for Modern Control 463-663. This homework set looks at canonical forms, similarity transforms, and LaGrangian dynamics. So the first part of the homework is given a transfer function, express it in controller canonical form. So to do that, we want the numerator and denominator polynomial. So in MATLAB, that's the function poly. That basically tells you what the A matrix is. The A matrix is 1 on the off diagonals, and the denominator polynomial in decreasing powers of s is here. So here's your 50 minus 65s plus 16s squared with minus signs. The B matrix is 1 in the last entry, and the C matrix is the numerator polynomial in decreasing powers of s, or increasing powers of s. So there's the 180 plus 150s plus 30s squared. As a check, if you throw that into MATLAB, store it in state space form, find the transfer function, I get the right answer. So that is one way to represent this system. Another way is in cascade form. So here what I'm going to do is take 3 first-order systems and cascade them. If I do it this way, to put this over common denominator, B has to get multiplied by s plus 1 over s plus 1. C is s plus 1 times s plus 5 over s plus 1 times s plus 5. So there's the numerator polynomial. That should be the 30 s plus 2 s plus 3. Multiplying it all out, matching terms, tells you that C is 30. Then I can solve for B. B is minus 30. A is 60. So in cascade form, here I always do over s plus 10. So it's the minus 10 cascading to minus 5, cascading to minus 1. That's cascade form. The eigenvalues are on the diagonal and 1 on the off diagonals. The B matrix, the input feeds the first system, that drives the second, that drives the third. The C matrix is your A, B, and C that you calculated. As a check, input that system into MATLAB, I get the same answer. So that's another perfectly valid way to represent the system. Third way is Jordan form. Do partial fraction expansion. I get 3 first-order systems. The A matrix is just the diagonal, pulls at minus 1, minus 5, minus 10. The numerators are the B matrix, and C is just 1, 1, 1. And actually B and C can be flipped. All that Jordan formula cares about is that the product of this term times this term is 1.667. This product, the second entry, is 9 and 37. As a check, throw that diagonal system into MATLAB, into state space form, find the transfer function, same answer. So there's an infinite number of ways of representing a system in state space form. Some have names, those are the canonical forms, many of them don't. Problem 4 looks at similarity transforms. Given this system, do a change in variable. Let z be this. So z1 is v1, v1 plus v2, and so on. So this basically is the inverse of the similarity transform. The similarity transform is z1 is v1, z2 is v1 plus v2, v1, v2, v3, and so on. So that's the inverse, t inverse. Take the inverse, this is t. What that is, it's x is equal to t times z, or z is t inverse times x. And that's the change in variable going from x to t. Once I've got the similarity transform, I can form the new system. Your new A matrix is t inverse AT. The new B matrix is t inverse B, C times t, D. So here's another perfectly valid way to represent the system, just with the change in variables. Problem 5 looks at block diagrams. We'll be doing this a lot this semester. Given a block diagram, put the A, B, C's, and D's together. So in this case, I would write the first equation, take Sx1, that's equal to A1 times x1 plus B1 times U minus B1 times C2 times x2, first equation. Sx2 is A2 times x plus b2 times c1 times x1 plus b2 times d1 times u plus b2 times d1 times minus c2 x2. The order matters. With matrices, multiplication is not commutative. If you get the order wrong, MATLAB will give you an error saying the dimensions don't match up. Get the order right, the dimensions should work if you put this in MATLAB. The output then is c2x2. In state space form then, your sx1 is a1 times x1 minus b1 c2 x2. Sx2 is b2 c1 x1, a2 x2 minus b2 d1 c2 x2. So there's the second term. The B matrix are the inputs, b1, b2 d1, and the C matrix is I'm looking at x2. So when I combine two systems together, here's how the ABCD combine to produce the net system when using this topography. Problem 6 is a little more complicated. Given two systems with a third system in feedback, now find the net ABCD matrix. So same procedure as before. Let's just do SX2. SX2 is A2X2 plus B2 C1X1. So we did this path, did that one, plus B2 D1U plus D2 or B2 D1 times minus C3X3 plus B2 D1 times minus D3 C2X2. Likewise for X1, likewise for X3. Now, to put this in state space form, SX1 is A1X1. Let's see, minus B1 D3 C2 X2 minus B1 C3 X3. Second equation, third equation. So this is how A, B, C, and D combine to produce the net system using this topography. The last problem. Now this is the fun one. Given a plane that has this shape, 0.5x plus sine of 2x, find the dynamics of the ball. And here what I'm trying to do is come up with this animation. If I can figure out how to get there. So here's the system I want to get to. When I simulate it, here's what it looks like. I'm calculating the acceleration at any given time, integrating once to get velocity, twice to get position, plot the position, and I can see the ball rolling back and forth in this bowl. So what are the dynamics? Well, the first step is to come up with the potential energy and kinetic energy. Potential energy is mgh. Kinetic energy is 1/2 mv squared, assuming a solid sphere. The rotational inertia makes that 0.7 mv squared. Mass is 1, so it's 0.7 x dot squared plus y dot squared. X dot squared is just x dot squared. Y dot, take the derivative of y, plug it in. That's y dot squared. Now do a whole bunch of algebra. Multiply out the square. Cosine squared of 2x is 1 plus cosine of 4x over 2 using a trig identity. Bringing the constant out. This term, there's a cosine 4x term. Okay, so when you're all said and done, I've got the kinetic energy right here. I've got the potential energy. Form the Lagrangian. Lagrangian's the difference in the two. The dynamics come from taking the full derivative of the partial derivative with respect to x dot minus the partial derivative with respect to x. Partial derivative with respect to x dot would be 2 times 2.76 x dot. That's this term. Here's an x dot, so it gives you 2.8 cosine 2x x dot. There's another x dot. 2.8 cosine 4x x dot minus the partial derivative with respect to x. Let's get this cleaned up. So no x's here, nothing. There's an x. The partial derivative would be minus 2.8 sine of 2x, x dot squared, minus 4 times 1.4 minus 5.6 sine of 4x, x dot squared, minus 0.5g, plus 2g cosine 2x. Goes to the partial derivatives. Now take the full derivative. For this guy, if I take the full derivative with respect to x dot, I get x double prime times everything else. Chain rule. Take the derivative with respect to the first term. The derivative of cosine 2x is minus 2 sine 2x x dot times x dot gives you an x dot squared. 2.8 times, we'll take the derivative, I get minus sine 4x times 4 times x dot times x dot gives you x dot squared. And then these terms just come down, just distributing the minus sign. These somewhat cancel, gives you minus 2.8. These somewhat cancel, gives you minus 5.6. It just comes down. So here's the dynamics. And wasn't that fun? If the force is 0, I can solve for x double prime. And I've got a sign error here. That's where I was having problems with my simulation. That's what I simulate. So in simulation, what I do, here's the start of the code. I'm going to start with my initial condition at minus 0.1. Let's see, for 5 seconds. Let's make that 10 seconds. I'm going to calculate the acceleration. That's this guy right here. There's the numerator term. There's the denominator term. The acceleration is numerator over denominator. Here is how far the ball is rolled. That's the square root of 1 plus x dot 1 plus x squared dx. Then doing Euler integration, I integrate acceleration to get velocity, integrate velocity to get position, integrate how far the ball is rolling to get angle, display it, and here's what it looks like. If I can find my display. There it is. So here's the ball rolling around the plane. And the nice thing about the Lagrangian formulation is it works. That's a big plus. It's a lot of work to get there, but at least you are able to get an answer. As far as I know, this is the only way to come up with the dynamics for something like this. But that's homework set number 3 for ECE 463-663.